Okay, so thanks for the attendance. Today we have Andrea Caputo, who's currently PhD student about to finish at IFIC Valencia. Andrea is about to move for a joint position at the Tel Aviv University and Weizmann. Today he agreed to give a talk with us at our seminar series about longitudinal plasmon-axion conversion in external magnetic field. Thank you, Andrea.
Yes, so thanks, Luca, and all the organizers for the invitation, and thanks you all for connecting. I really hope that you are all fine in this crazy period. And today I will be talking about this work that I've done with these two terrific young postdoc here, Alex Miller from Stockholm University and Edoardo Italiano that is now in UCLA. And you know, we are a very young crew, so any suggestion, any question, any hint is more than welcome. So just make a lot of questions and a lot of comments. And actually, I really like interactive talk. I usually give Blackboard talk. So I don't prefer to have question at the end. You can really interrupt me if there is anything not clear, and you know, make the things as much as interactive as we can. Okay, so today I will be talking about, as Luca said, longitudinal plasmon conversion into axion, into stellar environments. And this is my outline. So I will start with a brief introduction about the strong CP problem, although not a very long introduction. Then I will go through explaining some physics of plasma and dispersion relation of photons in a QED plasma. Then I will give the rate that we calculated for this conversion, that is actually a resonant conversion. And then I will show you the results for our calculation in the Sun and in magnetic white dwarf. And then I will go and conclude also. Actually, I will also be talking very briefly about a follow-up that we hope to finish soon with Charan OR2. Okay, so let's start with the strong CP problem. We know that the QCD and the Lagrangian of the standard model suffers from the strong CP problem. That is to say, in the Lagrangian, you can put a term like this, where G is the field strength of SU3, G dual is the usual definition with Levi-Civita tensor. And actually, classically, you can realize that this is a total derivative. So also for the students into the audience, you know, when you study electromagnetism, for example, you are told that if you can just omit FF dual in the Lagrangian because it's a total derivative, so it doesn't contribute to any observable. And that is okay for U1, that is an abelian group. But actually, the vacuum structure and the gauge configuration of SU3 makes this more tricky in this case. And actually, you have to keep this term, and more importantly, because we are doing physics, these terms also generate observable effect. And in particular, this to a dipole for the neutron, there were some very beautiful paper back in time by also Veneziano and Witten. And so you predict this dipole moment for the neutron, but then you go into the laboratory and you don't observe any. You just bounce. And actually, the actual constraint that we have is this one. So this parameter theta has to be smaller than 10 to the minus 9. And notice that this parameter theta is a dimensionless parameter. So we have a parameter that is very, very small. And so this is why it is called a strong CP problem. It's strong because it's associated with strong interaction. So with SU3, QCD. Is CP because it's CP violating. You can calculate, and using the property of the Levi-Civita tensor, you can see that it's violating CP. And it's a problem because we have this very small number. And you know, in physics, we don't like coincidence, right? When we see a very small number, we would like to have some dynamical explanation for it, some symmetry behind it, right? And so this is why this is a problem. And the most elegant, at least in my opinion, one of the few also solution to this problem is the Pesce-Queen solution and this diaxion that is connected to what I just said, right? I mean, you want some dynamical reason for this parameter to be small. So you promote this parameter to be a dynamical field. And this field is actually a pseudo-Goldstone boson associated with some U1, a new global symmetry that is called Pesce-Queen because of the two others, right? So you have this new global symmetry, you will break, and then you will have a Goldstone boson that actually is a pseudo-Goldstone boson because it acquires some mass through non-perturbative effects. And what it turns out is that essentially you end up with a coupling in the Lagrangian that is done in this way because of the color anomaly, and where Fa is the decay constant of this field that is called the axion. So this is the famous axion, right? And Fa essentially is the decay constant. It also regulates, is the scale of the breaking, if you want, somehow, and regulates all the strength of the interaction of this new particle. And actually you can, so at the end of the day, you can do the calculation, see that the mass is positive, and then this field essentially relaxes to zero. So you have a dynamical explanation for that parameter in the Lagrangian to be small, okay? So this is how you solve the strong CP problem. I mean, all this theoretical introduction won't be relevant for our work, but it's important to introduce it also because like it's somehow confusing in the sense that is this axion, and you notice that you have a coupling with the gluons, essentially, right? But then most of the experiment, if you're in the subject, they don't deal with this coupling. Also, we won't use this coupling here. Actually, we will use this coupling here, where this GA gamma gamma is just 1 over Fa with maybe some constant depending on the UV completion of okay? Where F is now essentially a coupling with the photon. And this comes out because of U1 electromagnetic anomaly. So what you can do, you write down your Lagrangian with your quarks, for example, and this term here, you do an axial space-dependent rotation, and then you see that this rotation is essentially, this transformation is anomalous, and then you have a shift in this term, and you also produce this coupling here, right? So most of the experiment, just to let you know, essentially use the coupling with the photons of the axion, this very peculiar coupling. And also for us, this will be the coupling that we will be using, okay? And actually, just for etymology, I will be talking about axion. If you prefer, sometimes you can call it axion-like particle, in the sense that it's a particle that doesn't solve the strong CP problem, but it couples to FF dual in this way. So it couples to the photon in this way. An axion, if you want. I mean, or people also define it broadly, but then it's you know, it's just etymology as you want, as you like. Okay. So after this. Okay, I will go a little bit in some explanation of plasma physics, because I will deal with axion in stars, where there's essentially you treat them as a QED plasma, and the important plasma, you cannot really think about what you usually think of to be a photon, like the usual dispersion relation omega equal k. Dispersion relation, because of the presence of the medium, is modified. Okay, the interaction of the background modified the dispersion relation, and at the end of the day, you will have some. Oh, what happened? Sorry. Okay, and at the end of the day, you will have a modified Maxwell equation that is this one. Okay, and where, let me explain you this equation. You have this term here that I hope you can see is the polarization tensors of the medium. Okay, and PA mu nu is are just the three projecture. Okay, in your basis, and PA are essentially the response of the medium to wave that are polarized longitudinally. This is when A is equal to L, or circularly polarized. These are the usual bases when you have longitudinal and then the two circularly polarized transverse way. And actually, you have a very nice treatment of all this physics. There's really a lot of physics inside here. And you have a very nice treatment. I suggest you the book by Georg Graffeld, Stars as a Laboratory with Fundamental Physics. It's a very nice book in which you have all this physics there. Now, the important thing is that, so when you have this medium, you now have three polarization for your photons. And this is somehow weird, right? Because you're used to have just two polarization because of gauge invariance. But then the point is that now you're breaking Lorentz, so you still preserve gauge invariance. You will have always your word identity, but essentially you will have your tensor. You are essentially the velocity of the medium, okay? What is usually called d mu, okay? And so at the end of the day, you will have two polarization that are plus minus, the transverse one, okay? And then a longitudinal polarization. And the longitudinal polarization, you have to think it just as a density weights, right? Of the medium, of electron. And it exists just because, okay? So, and then the important thing is that you have this expression here, and for each polarization, you can solve essentially this equation, and you can find your dispersion relation once that you have your polarization tensor, right? So what you should do, imagine that you are in a medium, that will be what I assume, what we call a QED plasma. That is to say, essentially a plasma made of electron and ion. Now, when you calculate the refraction index and all the polarization tensors, you can actually neglect the ions, because all the effects will be suppressed like 1 over the mass. So essentially, at the end of the day, you just have to calculate the effect of the electron, right? And you can do this calculation, and you calculate the polarization tensor in the longitudinal. Notice that if the medium is one polarization, transverse polarization for the two transverse modes. And actually, you can do this calculation very easily in two ways, essentially, that I've this. So at lowest order, essentially, what you can do, you can calculate the common forward scattering, okay? And then just weight with the distribution of electron and positron that are this function here. This is very important. You have to weight with the statistical medium in your plasma, right? The temperature, for example, and the chemical potential enters into the game, okay? Actually, another way to do this calculation is also very nice, is through thermal field theory. So you just calculate the loop, the thermal loop, the correction of the photon propagator, but now you're at a finite temperature, so when you do the sum over frequency, for example, if you work in imaginary space, imaginary framework, you have to sum over the mass by a frequency, as usual, okay? But the important message is this one. These are kind of complicated equations, right? And to find the dispersion relation, you should solve an equation like omega squared minus k squared equal this stuff here. So in principle, they're like difficult transcendental equation, right? But then most of the time in the literature is fine because you find some very easy dispersion relation for what people call plasmon, right? For example, and this is fine in some condition, but not always. So you have to be careful. You have to be careful. For example, now imagine that you are in what we call a classical limit. That is to say, a limit in which your plasma is non-degenerate. That is to say, also the density is not that large, and not relativistic. It is also to say that the temperature is not that large. For example, I will talk about the sun. The sun is a perfect environment to do this kind of consideration. So the dispersion relation in this case, you can find them, and there are these two kinds of dispersion relation. So for example, look at the first one, the transverse one. Forget about the correction in temperature. You have omega squared equal k squared plus omega p squared. Omega p squared is essentially the plasma frequency that I will show in a moment. It's a typical frequency of your plasma related on your density. And if you forget about the temperature, essentially, this is what we usually use, for example, when we deal with dark photon in the early universe, all this kind of stuff, right? What we say usually is that the photon acquire a mass, right? And this is right? The photon, of course, doesn't acquire a mass because gauge invariant is still preserved, but the dispersion relation is modified. And at the lowest order, actually, this is fine. And then you have the longitudinal. At lowest order, essentially, the longitudinal mode is just oscillating with an almost fixed frequency, okay? And this frequency is the plasma frequency, as I said, and is related to the density of the what I will say in the following. More formally, you can calculate the plasma frequency just doing the limit of k going to 0 in the integral that I showed before. And now there is a very important plot for what we did with Eduardo. That is the plot of the different modes in a relative. Okay, like for the sun, this could be, for small wave number, this is a very good picture. So on the x-axis, you have the wave vector frequency. On the y-axis, you have the frequency, omega, always normalized to the plasma frequency. And you see, first of all, that it's not, when k is equal to 0, you have the plasma frequency. It's just also the definition of the plasma frequency. And then you notice this is the normal photon straight line, right? The light cone. Then you have the longitudinal mode, because as I told you, in a non-relativistic system, essentially the longitudinal plasma is just okay. And then you have the transverse mode, that is this one, okay? And then I introduce another piece of information. I introduce a dispersion relation for a massive particle. This is the axion, sorry. So it's omega square minus k square equal mass to the axion square, right? And this is for low enough mass of the axion, in the sense that for low enough mass, like below electron volt, let's say, but even larger, it's not too. What you notice here that is crucial for us is that you always have a mode at which this dispersion relation of the modes. So essentially, you will end up with what I called a resonant conversion. Okay, and this is very important. So we will use longitudinal modes to produce essentially from a population of longitudinal modes, produce axion at resonance, essentially. So this also means that at the end of the day, you will also produce axion more or less with the frequency given by the plasma frequency of your longitudinal plasma. Okay, and this is very important because all the physics that I'm going to show is essentially coming from here. Okay, I think this is a good moment actually to take questions, because then I will pass to study two different setups like the Sun and White Dwarf. But I already gave you a lot of information about some physical stuff that is, at least for me, was not very well known before last year and studying it for a while. So if there is any question, please go ahead now. Also in the chat.
Question. What sets the frequency omega of the transverse mode when k equals 0?
Yes, okay, yeah, so this is a good question. In both cases, essentially, it's very important to take into, so if you go back to this integral, okay? So, and then you see that to get this, you have to do, in this integral, essentially, you will have to do a limit. So at the end of the day, also in this case, it's very important, the distribution of the electron. And at the end of the day, the introduces to the usual integral of the phase space distribution in which you get a density. So at the end of the day, the omega, that you have to start from this integral and then take some limits. And also, let me say that I was already living, let's say, in a particular scenario of the classical situation. You can actually find out different expression for omega plasma in different limit. And this also is very, I mean, the paper in the book by Georg, and also in this paper by Bratton and Siegel. Different limits, for example, what you find in the degenerate limit, what you find in the relativistic limit, what you find in the classical limit. In this case, it's very simple, essentially just the density of the electron at the end of the day. Okay. And then the mass and the coupling constant, of course, of the QED, but that is always there because you are doing forward scattering with just QED. Okay.
So the density of the electron, because there was some bug in the video, so I didn't hear you well at some point.
Yeah, I didn't. Oh, sorry. I didn't. Yeah, at the end of the day, you have to think about the omega plasma would be square root, roughly, of the density of the electron. So this means that, for example, when I will show you the results from, let's say, the deeper you go in the sun, the density will grow, and also the plasma frequency will grow. Okay, this is what you have.
But if you want a crossing between the transverse and longitudinal mode, you want omega for k equals 0 to be smaller than omega.
But you don't want a crossing of transverse and longitudinal. Here. You want a cross of the axion dispersion relation to the longitudinal.
I see.
You see, because here is like when you do also your narrow width approximation, right? When we do our collider stuff, right? You want to be in this resonance region to produce efficiently, if you want, these axions. Okay.
Okay.
So it's the axion that is crossing the longitudinal one. Okay, great questions. Any other question before I go ahead? Okay, I don't see any. So let's move to the first system that we considered, that is the sun. And no, actually, I will first very briefly tell you how it looks like, this process and this calculation, right? So, first of all, I have to say, I will show now the reference that this process we were not the first one to calculate. As many things in this field, like Georg calculated this first in 1998 in a paper with Michev, but we recasted into the framework of thermal field theory. Treatment on 1983. So the idea is to calculate. So the idea is this one. You have longitudinal plasma, and you want to calculate rate of production from this thermal bath of a weakly interacting particle that is, in this case, is the axion. Okay. It turns out that the rate of production has this very simple expression, and so all the calculation really amounts to calculate this object here. That is essentially the self energy of the axion. Then you cut it and you calculate the imaginary part of this diagram, and then you will have your rate. And we were very glad actually that we recovered. So this was the by in which they did this calculation and with different methods, and we fully agree with them. Luckily for us, and we get the same answer. And this is actually the answer for the energy loss. So essentially, the axion that you are producing per unit volume, per unit time, the energy of this axion, at a given, this is important, at a given radius of the star. Okay, because actually, notice in this expression, there are very important factors. So there is the magnetic field. And this is normal because in this, you see in this diagram that it enters the magnetic field. The larger will be the external magnetic field that you have. The larger, of course, will be the rate at which you produce these guys. Then you have, of course, the coupling constant, GA gamma gamma, between the axion and the photon. And then you have this very important, you have omega plasma square, cube, sorry. And then you have this very this Bose-Einstein factor, statistical factor, e to the omega plasma T, the temperature at a given radius, and the plasma frequency at a given radius. And this essentially is setting the population of the plasma. And this is very important. So if you have in mind that whatever application of what I'm talking about in environment, in astrophysical environment, you should first check that this is not this rate is not exponentially suppressed. If your plasma frequency is much larger, so it's super dense compared to the temperature, you're to produce anything, okay? So this is a crucial ingredient. And then a second crucial part is that this depends on the radius. So to get the total one, the total flux or differential flux, you will have to integrate in principle over all the star. So will be also crucial to have a good model for your star, right? Because you have to integrate over the volume of the star, so you will have to know the property of the star as a function of the radius, okay? And all the properties vary. The plasma frequency vary, as I was telling Jan before. For example, if you go deeper in the star, the density will be larger and the plasma frequency will be larger. Same stuff for the magnetic field. The magnetic field inside the sun will be much larger than on the surface, okay? Okay, so so this sets the stage of what is that is, you know, it's close, we know it more, so we thought that it was a good place to start with. And so you go here, and as I told you, you have to assume a model for your sun, right? So for internal property of the sun. So here, for example, you see the omega plasma frequency. You see that in the interior of the sun is like 300 electron volt, more or less. This is in units of keV, and then it drops at the external part of the sun. Then you have also the temperature here, and then you also have the D-Bay length. Actually, I didn't talk about the D-Bay length, but it's an important quantity because, for example, we will compare us with different processes that are like mediated by Coulomb interaction, like Primakov, Bremsstrahlung, and you know that there you have a divergence, and actually the screening of the medium cure this divergence, and so you have to take the screening into account, and the screening will depend also on the ions, because I told you that the plasma frequency doesn't depend on the ions, but the D-Bay scale does. So you have to have a model in which you also have all the abundances of the elements and everything like that to do all the calculation properly, okay? And so we use this model, and then actually the most uncertain part of all this stuff is actually the structure of the magnetic field, because it's pretty unknown. So what we did in this paper, in the paper actually we considered different possibilities. Our benchmark model is the model of the magnetic field that is given by some of the same authors of the Sackley model. So in this paper by 2008, and actually is a model that fits very well all seismology observations, and is, as far as we know, is one of the best model. But you know, I'm not an expert. We are not experts of solar physics. So if you have any model that we should try, just let us know. What you should know is that in this model, you essentially separate the sun in 3 zones. You have the internal part of the sun with a very, very large magnetic field. Then you have a tachocline that is a very narrow zone close to the convective zone. And then you have a pretty narrow, but not narrow as a tachocline in the external layer, in which the magnetic field is much smaller, like 3 Tesla or something like that. Okay? So these are our inputs, and after this we can do the calculation. And we did the calculation, and as the first thing, we calculate the total luminosity, right? As I told you, you integrate the formula essentially that I showed you before over all the volume. And of course, you have to compare with other processes that will compete, right? So the first process that you should compare with is Primakov, that is this diagram here. And if you look at all the paper, essentially, when you look at the sun, also if you look at CAST or YAXO prospects, you know, they always have in mind Primakov or Bremsstrahlung for maybe at lower energy, but mainly Primakov because it's really efficient in this classical environment that is the sun. And so we compare the calculation, and then that was very sad news, because here you have the luminosity as a function of the coupling, and the blue line is Primakov, and the red lines are actually 3 magnetic field model that we use. You can focus just on this. Actually, we computed it consistently. You can find fitted formulas also in their book or in other papers, but we computed it from scratch using our solar model, and it wins. And this is also why the sun in their paper, they consider supernovae, for example. And this is because like the total luminosity is just much smaller than Primakov, even for a large magnetic field. But then we thought, okay, after that you look for the total luminosity, there is another observable that you look for. It is the differential flux, okay? And for the differential flux, the situation is much better. So you have the frequency on the x-axis and the differential flux in these units here on the y-axis. And then I show 3 different processes. So the blue line is Primakov, and you see it from the sun. And so it's the flux at the Earth from the sun. And you see that it's peaked as usual at around 3 keV, more or less. The green line is the geoflux from the Earth. So geo, yeah, the axion flux from the Earth, calculated assuming a KSVZ model in which you produce, I will tell you this, like the electron coupling just via loop. And then there's a very nice thing, I think, of our work. 3 zones here, these red zones, they are our process. So these are the axions produced through longitudinal plasmon conversion within the seismic model of the sun that I showed you before. And you can really understand it, because notice this first peak. This first peak is around 100 electron volt and is precisely the plasma frequency into the interior part of the sun. So I see that maybe there is a question in the chat.
Yes, Andrea, can you hear me?
Yeah, sure, Victor. Yeah, please go ahead.
Can you repeat again? What is the geoflux?
The geoflux is the flux from the Earth, from the internal of the Earth, through Bremsstrahlung, okay, at the Earth. Okay. So actually, this is we didn't did the calculation, because actually it's an art calculation to do the Bremsstrahlung properly. So we just took some work by Patrick Huber, and so this is just Bremsstrahlung into the Earth, producing axion. So there you are not using the coupling to photon, you are using the coupling to electron.
I see.
And I will comment on that because it's also very important for the comparison that I will do with a very nice paper by Chris, by Benjamin Safdie, and Chris is PhD student in Michigan.
Okay, thank you.
Okay, and so yes, thank you for the question. Yes.
How do I understand that the Primakov process is not resonantly enhanced by the crossing of dispersion relation? Why do you have to go at second order in the axion-photon coupling?
No, you don't have to go to second order. It's just that when you do the Primakov effect, you actually find an appendix in our book. It's just let me show you. It's just this process here. It's really essentially a photon like scattering over the electric field, if you want, of the nuclei and the atoms into your arm. Okay, and this essentially here you are talking also about transverse photon and a completely different energy balance. You will have a different behavior, and the important thing is that the kinematics and the energetic inside there is completely different. So for example, in our case, we are really converting this longitudinal modes that they cross, right? While transverse, they do not, okay? So we are really converting them. So we are peaking at a frequency that is proper of those modes. While Primakov essentially is regulated by the other energetic of the, essentially, of the electric field of the motion and the photon of the plasma, right? of the charge that are moving in the plasma. Actually, in principle, you could also do the same with a magnetic field, but they are moving very slowly, so you won't have it. So it will be mostly electric field here. So it's a completely different process. You can do the computation that you also find in Georg Raffelt's book and in his previous papers or in our appendix, and it's really a normal like Coulomb-like scattering that you then regulate with the debye screening, and then you integrate over the statistical distribution, and that's it. Okay, and that regulates all the flux. Okay, it's a different process, but
you can see the difference is just Primakov is mostly producing thermal photons, so they're happening at the temperature, whereas our process is happening at the plasma frequency.
Exactly. Exactly. In fact, if you notice, the peak of the Primakov is around the keV. If you remember the plot that I was showing about the property, also the temperature of the sun was peaking around that, right? So you have, in one case, everything is set essentially by the temperature of this thermal photon. In our case, it's the plasma frequency. And this is also why our process is peaking at very lower frequency. And this is also why we had the idea of looking for the differential flux, because the energy is completely different. Okay? And then I think is actually, and this is related, is that if you observe the axion, it will be very nice, I will be very happy for my career. And the point is that you could really use the axion as we use neutrino to understand properties of the sun, because you will have this axion production essentially mapping the magnetic field. I was talking about these three regions, right? This first peak, you remember that I told you that in this magnetic field model, there was the internal region. So this peak is coming from the internal region, where the magnetic field is very large and the plasma frequency is around 100 electron volt. The second peak is coming for the tachocline region that is less dense with a less strong magnetic field. And then this peak is also coming from the external layer. So you see that the height of the peak is very small because the magnetic field in the external layer is very small. And also you peak around electron volt because the plasma frequency there is very small, is around electron volt. Okay, not 100 electron volt. And so this is very nice because it's twofold. Or you can map the structure of the sun, or you can also engineer yourself to look for different experiments, to look in this different frequency range. Okay, because for example, experiments like YAXO, they are thought to look in the X-rays at this energy here mostly. I mean, they mostly look for it, right? But then if you want to go at electron volt, maybe you want to think about something better, right? Maybe the optics will be easier. Okay, is there any question about this? Actually, yeah, you can go ahead. I don't care about time. I can just stop at a certain point. The important thing is that everything is clear. So if you have questions, just go ahead. Okay, I think there are not other questions, so I can go ahead. Actually, you can ask me about this later. So this is the preliminary results for YAXO, but I'm running out of time. So if you're interested, just ask me later. And this is an upcoming work. And after the sun, I instead want to focus about white dwarfs. So white dwarfs are very interesting stars, and for some aspects, they're even easier in the sense that are mostly isothermal. And I think that physically you can understand it because the conductivity, I mean, essentially the heating is just transmitted via the electrons, and the mean free path is very large. So it's really like being in a metal. So you're almost isothermal, and you're also degenerate. The typical density can actually be very large. These are the typical density. And also the plasma frequency, remember, the plasma frequency will be also larger. Here we will have a peak around the keV, not 100 electron volt. And also the temperature is larger and almost flat. And actually the computation goes essentially in the same direction. It's a little bit trickier because it's a degenerate system. So you have to be careful to modify your thermal field theory calculation to take into account the dispersion relation are modified, and but the physics is the same. Okay. And as before, you can use you need to use a model if you want to produce any trustable result. And so we asked very kind people to give us their model for the white dwarf, and they were very kind and very nice in providing us all the table of data that we needed. And these are the plot for the temperature that you need, like the temperature, the plasma frequency, and also here instead the axion production as a function of the radius normalize so here QR is the total flux when you integrate from 0 to the small r, normalized to the total flux that you would produce when you integrate all over the star. So this plot, just to make you simple, is essentially telling you that the most of the flux of the axion is coming from the very external layer of the star. Notice here that I plot just from 0.9, the stellar radius on. And this is why when you go deep into the star, essentially the plasma frequencies start to increase very much, as you can see in this plot, while the temperature at the end of the day is almost flat in the interior of the star. So essentially your population of plasmon will be exponentially suppressed. You remember that statistical factor 1 over e to the omega t, that will be very small. And then essentially you won't produce any sizable axion flux inside the star, okay? And then you can play the same game as before, and then you can calculate, okay, there's a question in the chat, probably. Okay, thank you for the question. Actually, I don't know very much about the model because I was not actually. I know much more about the solar model. You know, I know how they implement their stellar code to all. I don't know pretty much about white dwarf, and I will be very interesting to actually to know more and also to know if there are other models. I have to be honest, at the beginning, we were completely messing this up because we were thinking that the density was almost constant or like not varying too much. So we were assuming a constant density. And then in the very last stages of the process, we asked for this model. But I would be happy to discuss it actually, or even offline if you are interested, but I'm sorry that I don't know much about it. Sorry. Okay, but yeah, that is important actually, because this is really crucial because the suppression is exponential. So if you will have, for example, a different ratio between the evolution with the radius of the plasma frequency and the temperature, that could enhance or suppress your signal quite a lot. So that will be very important to know if there are other models and what we can test, because actually, as in the case of the sun, in the case of a discovery, this will be a very powerful tool to probe the structure of white dwarfs. And yeah, thank you for the question. But actually, apart from the uncertainty in these parameters, that is actually a bigger uncertainty, I think that is the most important, that as usual is the magnetic field. So there are white dwarfs that are called magnetic white dwarf, in which the magnetic field is very large, like larger than 100 megagauss or around that. And so what we did, we assumed essentially a constant magnetic field as the one that you measure at the surface. Also for this, we found paper in which the magnetic field inside the star seems to be much larger. So this will be, if you discover axion, this could rule out very easily such kind of models. I mean, there were models in the literature in which you predict the magnetic field into the interior of the star to be even 3-4 orders of magnitude larger than the surface, and then you should produce a very large amount of axion. Okay, and so this will be a very post-discovery check. And for us, what we did was just to assume a constant magnetic field of around 100 or 400 magnetic megagauss, following some magnetic field of some known white dwarf from Zeeman effect lines and spectral measurements. I hope that maybe with Gaia we will have a lot of other measurements, or and then this maybe can improve it. And I mean, a lot of other discoveries also of white dwarf. And as before, we have to compare with competing processes. And before, so the competing process, the Primakov. In this case, the competing process is the Bremsstrahlung. So actually, this is the same process that rules the geoflux, to reply also to Victor's question. And this process was studied in different papers by Nakagawa, by Alter, using thermal field theory techniques, and also recently, and Andrew, I think, and to use this kind of coupling. The important thing is that the flux of axion, due to this process, is due to this coupling here. So you see in this plot, in this diagram, is the coupling with electron. So in our case, the coupling is the coupling with the photon. In this case, the coupling is the coupling with electron. Okay. So we did the comparison. So this is the ratio of the two flux due to our process, plasmon conversion, versus the Bremsstrahlung process with this thermal spectrum from Bremsstrahlung, in a model in which we assume the electron coupling to the axion to be generated at one loop. So essentially you have, and also like a very electrophobic scenario in which if you have a coupling of the axion, then you will have something like 4 × 10⁻⁴ times the coupling of the to the photon will be the coupling to the electron. So you have a suppressed coupling to the electron, okay? And so what you see, you have, this is a function of the magnetic field. Of course, the larger is the magnetic field, the better it is for our processes. And actually there's another crucial stuff that is the density inside the star. So this is a density of 10⁶ to the core into the core, and this is a density of 10⁸. So actually, I have to say that in the model that we had, in the tables, the density into the core was 10⁸, so it was pretty large. So we scaled essentially the model to consider a core density to 10⁶ with the same behavior. And this is important because of what I told you before. If the density is smaller, it's better for our population of longitudinal plasma. So you can see for not very large magnetic field and like typical of magnetic white dwarf, a typical density for low mass white dwarf, actually the plasmon one can be the relevant process to consider. Okay, and this is important because actually gives you a way to break the degeneracy between the coupling to the axion, to the photon, sorry, and to the electron of the axion. And I tell you why, because if you have this production of axion, you can essentially do the same search that was indicated by Chris and Ben in this paper. So essentially what they consider in this paper was, you have a white dwarf, a magnetic white dwarf, into the interior of the white dwarf, you produce axion through the coupling with electron, okay? Then you convert the axion that you produce into photon through the coupling to the photon into the external magnetic field. And so you will have, at the end of the day, a flux of X-ray to the Earth. And they did some, I think that they already put some constraint with some X-ray data and some known white dwarf. But then the point is that if you assume Bremsstrahlung, you are putting some constraint or you are looking for a combination of the coupling to the electron that regulates the production and the coupling to the photon that regulates the conversion. While in our case, essentially also the spectrum will be pretty similar, but we will be sensitive just to the coupling to the photon. And this essentially will, in this kind of model like KSBZ, in which you expect a suppressed coupling to fermions, that would be very nice. And would be another astrophysical probes, possible probes of the axion. Maybe we were thinking about, contact new star people and maybe have some time of observation for some magnetic white dwarf. And that would be very cool to do a proper analysis then with real data. Of course, in this case, I have to say that it will be very difficult, at least in my opinion, my impression, to put any constraint. What you would look for is for a possible discovery. If you see a signal, then it's a very good indication. If you don't see a signal, then it's very difficult to put a constraint because, as I showed you, there are a lot of uncertainties in the magnetic field, especially. Okay, so this is how you should think about it. And this brings me to my conclusion, and then I will be very happy to take other questions. And so, in summing up, we studied the conversion of longitudinal plasmon into axion, into the Sun, and to white dwarf. And we found out that this actually gives a very nice peak of axion production, axion flux from the Sun that you would not expect if you just consider Primakov and Bremsstrahlung. And so actually now we are seeing what YAXO can do for that, and it's quite exciting. And we also we are also telling that essentially if you look for an analysis like the one that Ben did, you can hope to break the degeneracy between the coupling to fermions and coupling to photon using this process that is not that suppressed. And so actually I just want to mention also briefly that there could be other astrophysical environment to consider. We were also thinking about, for example, Neutron Star, and that will be very interesting. The problem with Neutron Star, I did some first naive calculation. The problem is that if you consider all the star, then inside the star, where the magnetic field is very large, the density is very large too, while the temperature is not so, at least in the model that I was considering. So the longitudinal plasmon population is super suppressed. And also, we don't know very much pulsar and neutron star interior. And so if this happens, essentially, you will just convert into the magnetosphere, and then your volume is really too small to have any sizable, let's say, flux to be detected. But you know, if you have any other idea, I think that is, we did also this work because I think that this is usually not considered process because most of the people just think about, you know, transverse mode of photons and usual conversion, while I think that could be interesting. And you know, many follow-up are coming, so stay tuned and please ask me whatever you want now. Thank you, I'm done.
Okay, thanks a lot for the very nice talk, very throughout this. Okay, I think applause is deserved. Other questions? We have quite some questions during the chat. Now it's time to open some discussion.
Yeah. If any question?
So I see there is another question. Okay.
Yes, Andrea, nice talk. I wanted to know more about Neutron Stars. So what happened there? It doesn't work?
It does work in the sense that you can always have this process, in the sense that you have you will have a plasma and then you will have your longitudinal plasmon. But there are two main issues. So first of all, we don't know a neutron star, and so that is a problem also to model the interior or even just the to some good extent the magnetosphere, although we know better the magnetosphere. And second of all, when you go inside the magnetosphere, so we saw that essentially there are a couple of ingredients to this to work properly. First of all, you need a very large magnetic field. So you can think, okay, neutron stars are just great, right? The magnetic field is very large. If you go inside the magnetic field, inside the neutron star, the magnetic field is even large, will be super large. But there are two problems for that. First of all, when you go to very large magnetic field, I don't know if our calculation does apply like straightforward. There may be some Landau levels consideration to do, although we are dealing with longitudinal modes, so maybe that doesn't matter, but still one needs to check. And second, and most important, at least in my opinions, although Eduardo doesn't agree, but is that the density, as as far as I know, in all the models that I check, is far larger. The plasma frequency is far larger than the temperature, and so the population of plasmon will be suppressed. This is why neutron star in principle it could work, but my naive impression is that it's not that promising. But I would be glad to work it out more properly.
Yeah, it's an interesting.
Oh, thank you, Jeremy, for coming here. Thank you very much. Yeah, I was replying to that chat.
Okay.
Yeah, I have one question.
Okay.
In the case
Oh, yeah.
of white dwarfs, did you compare the plasmon conversion with the Primakov coupling? Like
Yeah, but yeah, that is a very good question, actually. But that the Primakov is this is also why we compare with the with Bremsstrahlung and not with Primakov. But this is actually a very good question, because it's actually not very easy to understand which process you should consider, and this you just have to compute it. And it turns out the main process in such a degenerate system is Bremsstrahlung. So Primakov will be suppressed. This is why we compare with Bremsstrahlung. So when we have a rate of order 1, a ratio of order 1 with Bremsstrahlung, we will have order of magnitude larger than Primakov. And this is just because of the fact that you are in a degenerate system, and Bremsstrahlung there is not suppressed. By Primakov you have some suppression, and so Bremsstrahlung is the winning one, let's say.
Okay.
Please, Jan.
Hello.
Yeah.
So, so you talked about inside the any system, like you talked about white dwarf and that. So, what happens like if you apply this formalism to the cluster of galaxies? Like,
sorry.
if you apply this formalism for cluster of galaxies, something you know.
Actually. So first of all, for sure you can do all this kind of stuff and conversion really in every plasma. So in cluster of galaxies, in galaxies, even in the, we are thinking about some application maybe in the early universe, all this kind of stuff. I didn't check what happened actually in the cluster of galaxies. I would guess the magnetic field is very small. So, I mean, just to give you an idea, for example, when you think about the galactic magnetic field or the extragalactic magnetic field, for example, in the case of the galactic magnetic field, the magnetic field is like 10 to the minus 6 meters. The extragalactic magnetic field is even lower, like lower than 10 to the minus 9 or things like that. In this Gauss, okay, in this case, instead, we are talking about in the white dwarf 10 to the 8 Gauss. So if you consider, for example, a galaxy or whatever, you would have a suppression in the flux that would be, I don't know, 28 order of magnitude naively. So I would guess it is really suppressed. But in principle, maybe if you go into the early universe, you know, you have larger magnetic field, you have different plasma condition, you can work out something.
But there was a factor that depends on the R, distance from the center or something like that.
Yes, because that, yes.
So because the structure is very large in case of galaxy cluster or something like that. So in case of white dwarf, it's very small and compact object. So isn't it the effect of the length scale will compensate?
Yeah, actually, this I don't know. I don't think so. Also, because like at the end of the day, for example, if you think about the differential flux, because I think about it more properly than the total luminosity one. If you think about the differential flux, then you will have to integrate at every frequency. Essentially, your signal is coming from a given radius. That is to say, if you have your galaxy, the largest frequency of the axion will come from the very center of the galaxy. So the gain won't be that large. Actually, in galaxy, there is another further complication that you may want to consider. And actually, maybe also in our case, we should consider, but we didn't. In principle, you can have upwards and downwards fluctuation of the plasma density. If that happens, then you should also worry about the back, let's say, the back conversion, the conversion back of the axion. And this could be also important, for example, in cluster galaxy, when you can have a lot of turbulence and all this kind of stuff. So it's not trivial, and naively especially for the scaling of the magnetic field and the 28 order of magnitudes, I would say that is suppressed, but we can do a very easy calculation and find it out. Thank you for the question. It's a nice one.
Other questions from the audience? If not, okay. Ah, you die. Hi.
Sorry, I was late. I was in this workshop. It ran very late.
Yeah.
Oh, you prefer the workshop to me? That's very bad.
No, I prefer because I was talking about my work, so I wanted to be there.
I'm joking.
Most is come to your talk, but sorry for the.
You record it so you can.
Yeah, I'll watch.
Catch it up later. Yeah.
Sorry.
If there are no questions, I would thank Andrea for being able to join, for the great presentation, and for doing work.
Thank you all of you, and thanks for connecting, guys, and take care.
Thank you, Andrea. Very nice talk.
Thank you, Jan. See you soon.
See you soon.
Okay.
Ciao, Mauro. Take care all of you. Bye.
Bye. Ok, thanks Andrea.
Ciao Luca, ci sentiamo offline.
Ci sentiamo che sì,
Poi mandami le cose.
Il mio altro paper sui plasmon.
Ok.
Capire cosa di sbagliato lì. Ciao.
Ciao.
Bye, Uday.
Bye.
Ending meeting.
Yeah.